I guess you transferred, didn't you? Your transfer
Yeah.
come in, one of our transfer students, and I met Patrick actually the first time when he was working on another project with another physics major on a very mechanical design where you're looking at alternative ways to make bicycle chains, and even thinking about maybe a bicycle business at the time. I'm not sure. And so the next time around, I came in. He'd already started the project, and I think he was looking for a place to set up and work on a passion of his, which was skiing. So here's an example where students have come in with a project that related very closely with the passion they had outside of the class, and then was able to apply stuff that they learned in the program to what they like to do outside of like academics. All right, so.
So my project is the effect of mass density and ski geometry on ski performance. So basically, I measured the moment of inertia of a bunch of different skis and took into account their geometry and what they were meant for. So some background on ski construction. Every ski is going to be made out of the core materials, composite layers, sidewall, top sheet, and base. For my project, the most important were the core materials and composite layers, mostly because it affects the weight of the ski, which directly changes the moment of inertia. Most skis are going to be made out of mostly wood core. Sometimes they make it out of foam or some sort of combination to reduce cost. They also add stiffness or take away stiffness, which also affects skis, but not so much in my project. So there's a few different types of skis. Generally speaking, there's racing skis, which are meant to go really fast, obviously. Recreational skis, which if you've ever rented skis, that's probably what you rented. All mountain skis, and then powder skis. And there's two main factors that define what ski fits into which category. And that's going to be the waist width, so the width of the ski directly underneath the center of the boot, and then their rocker camber profile. So rocker camber is the shape of the ski. So camber is the traditional lift underneath bindings, and up until about 10 years ago, every ski was full camber. But then the idea of rocker started to get introduced, which is now in most skis that you're going to see out there. But camber is meant for tip control. So racing skis are still going to have all tip control, or all camber, because tip control is very important. They're also going to have a very small waist width, about 68 millimeters, because they're looking to minimize any contact. Recreational skis are usually going to be a little bit of rocker, but mostly camber. And I don't know if I mentioned, rocker is this banana shape down here at the bottom. It's also known as reverse camber, so it's just camber in the opposite direction. Recreational skis are going to be about 75, 77 millimeters underfoot. It's a very generic ski, meant for mainly ease than anything else. And then we have all mountain skis, which are going to be in the 85 to 105 millimeter range underfoot. They're going to have more rocker in them because they're going to be meant for a more versatile ski to go all over the mountain. And then powder skis are going to have very little to no camber in them because tip control isn't very important. What's more important is being able to rise above the powder, and it gives it more of a surfing feel, which is the whole idea behind rocker. And so moment of inertia is the measurement of opposition a body has to its rotational speed about an axis. So if you think of, if you've ever spun around on like a rotating stool or something, and you stick your arms out, you move slower. You stick your hands in, you move faster. You're basically changing your moment of inertia, and it has a lot to do with mass density. So this top equation here is the general equation for moment of inertia. This middle one is what I use to find moment of inertia for different skis. And I did this by putting a ski on this rotating platform here. It's hooked up to a pulley with a known mass. Underneath the platform, there are these little wooden pegs that pass through a photo gate that measure the tangential velocity. From there, I can find the angular velocity and then take the derivative to find the angular acceleration, which is my one variable in my equation. And And so the reason this affects skis is it's going to affect your turning a lot. It's going to affect how easy it is to turn, how quickly you can turn. Also, if you're a park skier, it's going to affect when you're spinning around, going off jumps and everything. So basically, I kind of guessed at the beginning that smaller, fast skis meant for faster turns, like racing skis, are going to have a much lower moment of inertia than powder skis, where turning quickly isn't as important. So some things that are going on with the ski industry and moment of inertia. Here's an example of one way that ski companies are changing the moment of inertia. Rossignol recently developed something called air tip technology, where they have holes in the tips to lower mass in specific areas. And the way moment of inertia works is the more mass is closely centered to the axis of rotation, the lower the moment of inertia is going to be. So less mass on the tips inherently lowers the moment of inertia of the ski. Also, other companies will do fin tips to try and do that. Bindings positions also affects the moment of inertia. Generally, skis are going to have their bindings a little bit back from true center, but park skis, for example, their bindings are going to be directly in the center, which lowers their moment of inertia also. It also makes the ski more symmetrical because they land backwards, frontwards, doing everything. And then core material also affects it because weight is a huge factor as well as length. So here are the skis that I tested. We got the Vocal T-Rock. It's 164 centimeters. It's actually a telemark ski, so it's naturally lighter than a lot of other skis. Telemark skis are always lighter and more flexible. It's a waist width of 87 millimeters, so it's just into the all-mountain range. Then next I have the Solomon Scrambler. It's 165 centimeters long, 75 millimeters underfoot, so it's a recreational ski. It's also a foam core ski. It's not a wood core. All the rest of the skis I tested were wood core. And both of these skis were made before rocker was really a thing in the skiing industry. So these are both full camber skis. There's no rocker in them. Next I have the Moment PB&J. It's another all-mountain ski. It's 101 millimeters underfoot, so it's a bigger all-mountain ski. It's also longer, 172 centimeters in length. It does have rocker camber and then rocker in the tail as well. And it's another wood core. And then I have the Rossignol Experience. It's a rental ski, 174 centimeters tall, 77 millimeters underfoot, so it's another recreational ski. This one is a recreational ski that does have some rocker in it. Not a whole lot, but there is some. And it's also a wood core. An important thing to note about this ski is that it's naturally heavier than its retail version because it's meant to be durable because it is a rental. You can see here, there are these really big edge guards on the tips. So like I was saying before, instead of taking away from mass on the tips, they add it because being very technical in these skis isn't something you generally do. It's more for renting skis for a day or something. And then I have the Experience 88, another all-mountain ski, 88 millimeters underfoot, 180 centimeters tall, so it's a little bit taller. This one does have rocker camber as well, and it is a wood ski. This does have the air tip technology just in the front tip there. So they did try and lower the moment of inertia a little bit. Next I have a Rossignol powder ski. It's 106 millimeters underfoot, so just into the powder range. Also 180 centimeters tall. The main difference is, besides the size, is that they also have the air tip in the tail. So they have the air tip in the toe and in the tail. And you can see in the tip up here, it's a lot bigger than over here. There's a lot less mass up there. And it's also important to note that the Sol 7 is a lot lighter. Not a lot, but it is lighter than the Experience 88, which already makes you think, since they are the same size, that it's going to have a lower moment of inertia. And then the last ski I tested was a really big powder ski. It was the biggest and the heaviest ski I tested. It's the Moment Night Train, 186 centimeters tall, 123 millimeters underfoot, so it's a lot wider. This one has no camber in it, because like I was saying, tip control isn't very important. In powder, they're looking for more of that floaty, surfy feel. So it's going to be rocker and then flat underfoot and then rocker in the tail. And it's also wood core. So here are my results. The Vocal, the telemark ski, came in with the lowest moment of inertia, which makes sense. It was the shortest ski I tested, and it was also the lightest ski. Next, the Solomon Scrambler, which was that recreational ski, which already kind of fits what I thought would happen. The first thing that didn't fit was this Moment PB&J, the all-mountain ski, came in underneath the rental. But there are a couple reasons for that. First off, the PB&J had really big touring bindings on it, and if you don't know what they are, they're basically, it's not important what they do, but they're a lot heavier than regular bindings, so that means more of the mass proportionally is closer to the axis of rotation, which makes it have a lower moment of inertia. Also, the rental had that extra weight on the tips and throughout the ski, which would raise its moment of inertia. And then next is the Sol 7, that Rossignol powder ski, which did come in underneath the Rossignol Experience 88, which absolutely makes sense. What I was surprised was that the Night Train, the biggest and heaviest ski that I tested, didn't have the highest moment of inertia. And I think it's similar to the PB&J. It also had touring bindings on it, so that changed the moment of inertia, as well as the Experience 88 was missing bindings, which would lower the moment, or raise the moment of inertia and make it appear higher. So, based on my information that I found, I made kind of a rough guess about what the ideal moment of inertia would be for different types of skis. It was hard to do with the skis that I was limited to testing, but from my data, I concluded that for an all-mountain recreational ski, it would be around 0.41 kilogram meters squared. The rental came in at about 0.51. I think if I was more accurate with my testings, the all-mountain would have been a little bit higher, maybe about 0.51. The powder skis came closer to 0.6, with 0.58 kilogram meters squared. So that's where I came with that. So further study, obviously I'd like to do more conclusive testing. I was limited to what skis I can test with what I could get my hands on, so I was only able to get my hands on those 7 skis. But I would like to test a bunch of different all-mountain skis, a bunch of different powder skis, a bunch of different of the same type of skis, and the same length of skis. Because if you look at my graph, pretty much except for the 88, it goes in order from shortest to longest. So the biggest factor seemed to be the length of the ski. So the shorter skis had a lower moment of inertia than the longer skis, with the exception of the Experience 88. And yeah, and so some other tests that I'd like to do is test the moment of inertia about the longitudinal axis. So instead of testing through the axis like that, the axis would be like here. Because if you think about it, when you're turning, you are rotating the ski about that axis as well. So it definitely plays a part in the way you turn. And then also testing the flex of the ski, which is a huge part of what the ski is meant for. You're going to want stiffer or less stiff skis depending on what you're doing to give it more or less pop. And then all this studying could be used in new designs for skis, even possibly a variable moment of inertia ski, where the moment of inertia changes whether you do it or it does it automatically for what you're doing when you're turning or not. And that could be as simple as something that can move mass further or closer on the ski to your foot. So in conclusion, I need more accurate tests. But for the most part, lighter skis and shorter skis had lower moment of inertia, and vice versa. But I believe if I'm able to control all of my variables properly, that skis with a larger waist width and more rocker that are meant for longer turns, such as powder skis, will have higher moment of inertia than skis like racing skis or recreational skis that are meant for shorter turns. Maybe more speed is involved in that. And yeah, that's my presentation. I just wanted to thank Santa Rosa Ski and Sport and Christian Hodson. They lent me a bunch of their skis, and Steve Anderson and Professor Qualls helped me set up the presentation.